Hello and welcome to the Chapter 3 podcast on Section 3.6. Today we're going to be talking about balanced equations. So balanced equations, besides just satisfying the law of conservation of mass, we can actually use them for other things. The coefficients in a balanced equation basically indicate not only numbers of particles or atoms, but also the amount of moles. So if you look at this table down here, you can kind of see our balanced equation related to water, and we can relate it in terms of, see how the coefficients directly relate in terms of formula units, in this case molecules, and also in moles. But notice how the ratio isn't maintained for mass or AMUs. So remember, when you're using balanced equations, you cannot use masses in relation to these ratios from here. Okay. What this also tells us, it tells us the relative amounts. It's almost like a recipe, for instance. The proportionality is shown here. So for every 2 parts of hydrogen added to every 1 part of oxygen, you get 2 parts of water. So and that's true for molecules and moles. But again, notice how the masses and the AMUs correspond to the coefficient times the molar mass of our individual substances here. In terms of being able to use these ratios in conjunction with masses of substances, we can do stoichiometry. Okay, and here we have a couple flow charts to kind of explain what ratios we're going to use. To go from grams of reactant to moles of reactant, we use a ratio involving the molar mass in 1 mole. To go from moles of reactant to moles product, however, we need to use a different ratio, and the ratio that we'll use for this area here will be the balanced equation itself. And then going from moles of product to grams of product, we would use the molar mass of our product over 1 mole. And this is kind of illustrated in the second example. Again, explaining what's in between the arrows are what your ratio should be for your dimensional analysis. Here's a more specific example. So if we're burning or oxidizing glucose, 1 gram of it, how much water would we expect to get? This is a combustion reaction, and what's not shown here is the actual balanced equation. We would also need that in order to solve the problem, so keep that in mind. So this series of steps, if you follow the arrows, kind of highlights what you need to do. Again, you cannot directly calculate from glucose mass to grams of water. Just can't do it. So the first thing we would do in order to use the mole ratio from a balanced equation is convert our grams of glucose into moles. So we multiply by 1 mole over the molar mass, which gives us a number. And then this 6-to-1 thing comes from the balanced chemical equation, which isn't shown, which gives us moles of water. But we don't want moles of water. They ask for grams of water. So we multiply by the molar mass of water over 1 mole to get the units that we want. And again, we'll be doing some of these in class soon. What mass of oxygen is consumed in the combustion of 1 gram of C3H8? So this is another example. Again, here's our reaction. A lot of times you might have to complete the reaction and balance it yourself. The balancing is important, so we know what the proportionality is between oxygen and the C3H8. We start with our given over 1, just like we do whenever we do a calculation. We multiply it times the molar mass, 1 mole over the molar mass. Notice how grams of C3H8 cancel out. Now that we're in moles of C3H8, we can actually use the 5-to-1 molar ratio in the balanced equation, which is where this comes from. So 5 moles of O2 are required for every 1 mole of C3H8. If we stop right here, our final answer would be in moles of O2. But we want grams of O2, so we use the molar mass of O2 over 1 mole, giving us our final answer. And that is it for now.